YouTube channel. My chat here. Righty. Okay, Chemistry 3101. Well, we kind of ended off somewhere around here solving this problem about formation of a halohydrin, which we said was anti in terms of its stereoselectivity. And then we said the hydroxyl goes to the more substituted carbon in terms of regioselectivity. And so now we're going to turn our attention for the next two sections. We're going to discuss dihydroxylation. In section 8.11, we cover anti-dihydroxylation, and then in 8.12, we cover syn-dihydroxylation. And so this is the only time we learn both methods. We learn syn and anti-dihydroxylation. Anyhow, so if you're wondering what is dihydroxylation, it's exactly what it sounds like. You're adding two hydroxyls, one to each carbon of an alkene, and you form what we call a diol. And if you do it with ethylene, you form ethylene glycol. Sometimes you might hear diols referred to as glycols. And ethylene glycol is the major component, like I told you, that's found in antifreeze. So antifreeze is where we find ethylene glycol. And the anti-dihydroxylation is actually a two-step process, okay? Step one is to use RCO3H. So that is a peroxy acid. We call that a peroxy acid. And then in the second step, that's just aqueous acid, which you recognize. And you probably notice that there's a new functional group here, that when we take the alkene and treat it with the peroxy acid, we end up forming an epoxide. And that's a three-membered ring that has an ether in it. So let's take a look and dive into this deeper. Now, the first step, they show you a mechanism here, which is a completely concerted mechanism. All right, remember concerted just means all the steps happen at once. So this is a concerted mechanism. I will not ask you this mechanism for the formation of an epoxide, but you should know that step one, the treatment of the alkene with a peroxy acid gives you an epoxide. Now, if you're wondering, what are the peroxy acids that I can use? What is my RCO3H? There's two possibilities. You can either use peroxyacetic acid, or you can use this one here, which is metachloroperbenzoic acid, or metachloroperoxybenzoic acid. They mean the same thing. Anyhow, the one that my students tend to choose the most is this one here, and I think it's because they like acronyms. And so for this one, as you see down here, we write MCPBA, so metachloroperoxybenzoic acid. So that's your peroxy acid. That forms the epoxide. And I do think you should know the mechanism for the second part. And you're like, well, that's weird. Yes, you only need to know the mechanism for the second part, okay? And the reason why is it's just so relevant, right? What happens is that after you have the epoxide, so here's your epoxide, you treat it with H3O+, right? Remember, the first step is RCO3H. That forms the epoxide. And in step two, you just treat it with aqueous acid. And that is what is being shown on this slide. So we treat it with aqueous acid, and that protonates the oxygen of the epoxide to make an oxonium. And what that does is it renders these carbons extremely electrophilic. And so water is going to come in and act as a nucleophile, and we get an anti-addition. Why do we get anti-addition? Because it's going to attack the least hindered face of the molecule, least hindered face, so that we get anti-addition. And of course, there's a proton transfer at the end to restore neutrality to the molecule. So you get the anti-addition, and then you're also going to get the enantiomer. So in this case, you end up with a pair of enantiomers. Now, you probably noticed that we've looked at three-membered rings a few times, haven't we? We looked at a bromonium ion. We looked at a mercurinium ion when we talked about oxymercuration, demercuration. And now we're talking about a protonated epoxide. What do all of these have in common? Well, not only do they all possess a three-membered ring, but they all have a +1 formal charge. Right, we see a +1 formal charge in each one of them, and that makes the ring very, very electrophilic. So all of these rings are extremely electrophilic, ready to pop. And so all of these yield anti-products because the nucleophile is going to attack from the backside, just like in an SN2. So with that in mind, it says here, predict the products that are expected. Each of the following alkenes is treated with a peroxy acid followed by aqueous acid. And so this is going to be the formation of, or anti-addition of, formation of dihydroxyl compound or a glycol. Anyhow, so let's, I'll stop tripping over my words here. So in step 1, so remember, it's 2 steps. The first step is to treat it with the peroxy acid, right? And the second step is to treat it with hydronium. I'm going to write the steps out individually just so we can get some practice in writing out the intermediates. Okay, so in the first step, we're going to treat it with the peroxy acid. Remember, I told you don't have to know the mechanism for this reaction. All right, so we're going to form the epoxide. So let's draw the epoxide. So here's our 5-membered ring. We're going to draw the epoxide. It's only going to be on one face of the molecule, right? Because it's a 3-membered ring, so that means the 2 methyl groups are going to be going down like this. And then in the second step, we're going to treat that with aqueous acid. And keep in mind, this is a symmetrical compound. The compound that the epoxide is symmetrical, and so there's no differentiation in terms of the nucleophilic attack here. And anyway, you're forming a diol, so it wouldn't matter anyway. So we're going to end up with something that looks like this. So we're going to have one hydroxyl group going up. We're going to have the other hydroxyl group going down. So that means this methyl group is going to be going up and this methyl group is going to be going down. And then we're also going to produce the enantiomer. All right, same thing in the next one. I'm not going to draw the epoxide in this one. I'm going to do it a little faster. I'm going to say step 1 is treatment with the peroxy acid. Step 2 is treatment with aqueous acid. And then we end up with something that looks like this. So we get one hydroxyl group going down. We get the other hydroxyl group going up like this. So that means the methyl group is going to be going up. And then the proton is going to be going down on the other stereocenter. So something that looks like that. And so we're going to get this compound plus its enantiomer. So there you go. So this is anti-dihydroxylation. So again, just to rehash, these 2 steps is anti-dihydroxylation. All right, so that covers anti-dihydroxylation. Now we're going to look at syn-dihydroxylation. And I'll just level with you. Our book goes over way too many methods to do this, but I think he's trying to, kind of give you a rationale for some stuff here. So the first thing you're going to do with syn-dihydroxylation, or the first reactions that are mentioned, are a couple of 2-step processes, okay? First thing is you take your alkene and you treat it with osmium tetroxide. So step 1, I'm going to write it over here on the left. Step 1 is to treat the compound with OSO4. Okay, and that forms what's called a cyclic osmate ester. Okay, then once you form that cyclic osmate ester, you can treat it with 2 possibilities. Okay, the first one here, this is sodium sulfite and water, and on the bottom we have sodium bisulfite and water. So you can do either one of those. So what that means is you've got step 1 is osmium tetroxide, step 2 is sodium sulfite and water, or you can do this. You can do osmium tetroxide in the first step. In the second step, sodium bisulfite and water. Okay, either one of these do the same thing. They do a syn-dihydroxylation. So both hydroxyls end up on the same face of the molecule. Now, the problem with this reaction is that you need a stoichiometric amount of osmium tetroxide. If you're saying, well, what's stoichiometric? It means if you have 1 mole of the alkene, you need to have 1 mole of osmium tetroxide. And osmium tetroxide is extremely, extremely toxic. Britney Spears wrote a song about it. So it's extremely, extremely toxic. And so if we can avoid using osmium tetroxide, we will do it, okay? Because it's so toxic. I even worked with somebody who refused to work with osmium tetroxide, okay? So that's how bad it is. So is there a workaround? And the answer is yes, okay? Instead of using a stoichiometric amount, you can use a catalytic amount. So catalytic amount means maybe just 1 drop or 0.01 mole percent or 0.1 mole percent. So a very small quantity of it, and you use what's called a co-oxidant. And there's 2 possibilities for co-oxidants. You can either use this thing here, which is called N-methylmorpholine N-oxide. So that's NMO. So I'll write that down here for you. So it's N-methylmorpholine N-oxide. And this is a functional group we don't cover in this class. It's called an N oxide. Anyhow, don't worry about that right now. But you use NMO as a co-oxidant, or you can use tert-butyl hydroperoxide as a co-oxidant. So that's this compound here. This is tert-butyl hydroperoxide. Okay, so either one works. Osmium tetroxide, catalytic amount, and you can use NMO as your co-oxidant or tert-butyl hydroperoxide as your co-oxidant. I'll just level with you. My students almost always pick osmium tetroxide, and they'll write the catalytic amount of it, and under the reaction arrow, they'll put NMO, which is the co-oxidant. Okay, this seems to be what my students have really liked over the years, and it might be because the textbook uses it the most in the solutions manual. I'm not sure, but they love it, so I tend to stick with it too. There is another way to do a syn dihydroxylation, and that's to use potassium permanganate. So the reaction conditions, they're not even written on here, but the reaction conditions using potassium permanganate look like this. We use potassium permanganate and sodium hydroxide, so KMnO4 and sodium hydroxide. And then you have to do that at a cold temperature. So usually we just write on the bottom, you just write cold like this, okay? So that's being shown here. And it does something kind of like, you know, with the osmium where you form that, that ringed intermediate, the cyclic osmate ester. Here you form this permanganate cyclic compound here, and then you treat it with sodium hydroxide, and you get the syn dihydroxylation. The problem with this reaction is that KMnO4 is great in that it's not super toxic. It's really cheap, but the problem is that it reacts with many other functional groups as well. And so usually you wouldn't go to the cupboard and reach for the KMnO4 because it's just so dang reactive. So again, usually my students will pick osmium tetroxide, a catalytic amount, and NMO is their preferred method of syn dihydroxylation, and I don't take any exception to that one bit whatsoever. Now, if we look at these practice problems here, this is from question 8.31, and I recommend doing the whole thing. Okay, it's one of the practice problems that I have in the suggested practice problems. It kind of gives you, he throws the whole gamut at you. He throws every single possible way of doing syn dihydroxylation at you. So Hannah, let's take a look at the first one. So in A, we've got trans 2-butene, and we're going to hit this with OSO4 catalytic amount. Son of a gun. Mr. Dion, what are you doing? There we go. And then NMO. So is this going to be a syn addition or an anti-addition? It's not a trick question. Anybody? Is this a syn addition or an anti-addition? It's syn addition, right? So we're going to end up with something that looks like this. Right, where you have one hydroxyl coming up and another hydroxyl coming down. Let me ask you, is this a meso compound? Yes or no? And it's not, I'm not trying to fool you. But is this a meso compound? Exactly, it's not a meso compound, is it, right? Because if you rotate this bond, okay, 180 degrees, what you're going to end up with is you're going to end up with this. Oops, you're going to end up with this, where you have one hydroxyl coming out and you have the other one going back. So this is not a meso compound. So you end up with this compound plus it's an enantiomer is what you end up with. All right. If you were to take cis 2-butene, right, if you took this compound and treated it with osmium tetroxide, a catalytic amount followed by NMO, in that case, you would end up with a meso compound, right? You'd end up with something that looks like this. Okay, so this is a meso compound. So for the first one, we end up with a pair of enantiomers. For the second one, we end up with a meso compound. Does that make sense to everybody? This wasn't part of the question, but I threw it in here to kind of cover that subject a little bit. Cha? All right, let's try B. So this is A. And then in B, we have propylene, and we're treating that with osmium tetroxide. And then in the second part, we're treating it with sodium bisulfite and water. And that does a dihydroxylation. It's going to be a syn dihydroxylation. So we end up with one hydroxyl going up. This one is not on a stereocenter. And so we end up with this compound plus its enantiomer. And then on the last one, we're treating cyclohexene with KMNO4, sodium hydroxide. Oh, come on, sodium hydroxide. And you do that at cold temperature to prevent it from reacting with everything in the universe. And that will give you a syn dihydroxylation. So we'll put both of them going down for a change. What kind of compound is this? This compound that I drew at the bottom. What kind of compound is that? Exactly. Thanks, Kiana. Thanks, Eric. It's a meso compound, isn't it? Yes. 100%. It's a meso compound. All right. There we go. So let's get into the very last reaction in chapter 8, which is oxidative cleavage. And I think it is skill builder 8.8. It's very rare that I mention a skill builder, but this is one of my students' favorite skill builders in all of organic chemistry. And I'll show you how to do it. It says you can cleave a double carbon-carbon double bond with ozone followed by DMS. Okay. So if you're wondering what the heck is DMS, well, he was a rapper. No, I'm kidding. But anyhow, DMS stands for dimethyl sulfide, which is this compound here. Is a very, very smelly compound. I mean, one of the most stinky compounds I can think of. Okay. Anyhow, I could go on some stories about dimethyl sulfide having a horrible odor. But anyhow, what happens is you end up taking your carbon-carbon double bond and you end up breaking it like this, and you put an oxygen on each end. So in this case, you ended up with a ketone and an aldehyde in this particular case. Okay. If it's a tetrasubstituted alkene, then you get two ketones. But I don't ask the mechanism of this. You should know the Lewis structure of ozone just because you would have covered it in General Chemistry 1. But I will not ask you this mechanism. So will not ask mechanism. All right, the formation of the molozonide and then the ozonide. I don't cover that. The only thing that you would want to know is besides using DMS as a reducing agent, you can also use zinc and water. So I'm going to pencil that in here. So here for step 2, you could use ore, zinc, and H2O. Like that. So if we go over to a blank document here, just for a sec, okay. All right, so what we do for that skill builder is, let's say you had a problem, I don't remember what the compound was now, but you could maybe elongate the alkene, make it kind of really long like that. And what they did in the skill builders, they said, okay, so you're treating it with DMS, and then son of a gun, with ozone, and then DMS in the second step. And the way the skill builder works is like this. They said to draw the products, you take the starting material, copy it, just redraw it. So I'm just going to do it like this. Then you take the eraser from your pencil and you just erase like that. And then you put an oxygen on each end like that. And there you go. Those are the products of the reaction. Now, if you're looking at that going, Mr. Dion, that looks ridiculous. I agree. I don't like it when people draw that on a quiz. It's pretty funny looking. But it gets the point across that these are the products, right? You end up with this compound, and then you end up with this compound, okay? Give me a thumbs up if you follow me on that. That's how you draw the products of an ozonolysis. You're probably thinking, I wish they were all like that. I kind of like that. Just erase it, throw a couple of oxygens in there, put one here, put one there. Anyhow, and there you go. So that's how you draw the products of ozonolysis. I've seen ozonolysis come up on just about every final exam I've ever seen in my life in organic chemistry. So very important reaction. Now I lost my place, which was way, 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 way down here somewhere. Just bear with me and I'll find it. Nope, that's not it. So where were we? We were right here, okay? And I told you that I will not ask you the mechanism of ozonolysis. But we could look at a practice problem like this one, and it says, draw the bicyclic product that you would need, to make this compound. So, this is actually kind of an interesting problem. First of all, again, this is dimethyl sulfide, this compound down here. So this is DMS here, dimethyl sulfide. Let's just take a quick break here for a second. So something that I don't know if I've addressed with you a lot in this class, but when it comes to organic chemistry, when it comes to forming rings, because they're telling you it's a bicyclic product, a reactant, sorry, the rings that are most favored in organic chemistry are 5 and 6-membered rings. Those are the most stable rings in organic chemistry. If you have 5 atoms in the ring or 6 atoms in the ring. And so it's saying, if you were to make a bicyclic product. So the reason I bring that up is sometimes students will say, well, I'll just connect, and make a double bond between here and here. Well, that would be a 4-membered ring, which would be unfavored. If you made a ring between this carbon in yellow and 1, 2, 3, 4, 5, 6, between here and here, then you'd have a 6-membered ring, right? And if you did it here, between here and here, so 1, 2, 3, 4, 5. Then you'd have a 5-membered ring. So you have a 5-membered ring tied to a 6-membered ring. And so it would look something like this. I'll just kind of help you out with this one because, it's kind of tough if you're just learning the subject to draw this immediately. But if we start numbering, let's say we number here. We go 1, so maybe I'll do it like this. I'll go 1, 2, 3, 4, 5, 6. So there's going to be a double bond, right, between carbons 1 and 6, okay? So I'll number it like this, 1, 2, 3, 4, 5, 6. So that means there's going to be a double bond right here. Now I'm going to erase this because it looks ridiculous, okay? Get my object eraser, there we go. So that looked a little bit crazy, okay, the way I had it drawn. So between carbons 3 and 4, you see how carbon 3 and 4, on carbon 4, if I connect, I've got 1, 2, 3. So I'm going to have a ring tied between carbons 3 and 4 that's going to have 3 atoms in it. So I draw here 1, 2, 3, and the double bond is going to be between the carbon, the blue 3 and the red 3. That's the first time that's ever happened to me. So there is the bicyclic compound that you would have to treat with treat with ozone followed by DMS to get this compound here. Give me a thumbs up if that makes some sense now that you see it. Does that make sense to anybody? Okay. So all we're doing is this. If you take this compound, if we copy this, we paste it, I don't know, here maybe. Okay, all I did was this. I took my pixel eraser, okay, and I said if I was to break this here, and if I put an oxygen here, 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 okay, which looks kind of ridiculous, okay, but this compound now is identical to this compound. It's just not drawn in a stable conformation. Okay, so that's what you're doing there. So it's kind of a challenging problem, this one here, but there you go. Let's try something that might be a little bit more straightforward for us. It says predict the products expected when each of the following compounds is treated with ozone followed by DMS. So we treat this with ozone in the first step and then DMS in the second step. So what I'm going to do is I'm going to redraw this compound and I'll make the bonds really big. Like this, okay? Now we got this guy here, like this. So I'm going to get my eraser, make an eraser line here, an eraser line here, and I'm going to end up with one. Oops, where's my oxygen? There we go. I end up with this, 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 and this. Okay, so let's draw these products. Well, one of them you can see is just this. Okay, that's called acetaldehyde, and the other one, let's count the carbons. It's going to have 1, 2, 3, 4, 5, 6, 7, 8 carbons in a chain. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8. We're going to have a double bond to oxygen at carbon number 2. At carbon number 4, so 1, 2, 3, 4, 5, 6, 7. And there you have it. So those are the two products right there. Give me a thumbs up if that makes sense to you, or stop me if you have a question about that one. Okay, does that clear? Hopefully that clears it up a little bit. Okay. All right, so I'm going to erase this. Let's just delete all this for now. And then for the next one, we're going to do the same thing. We're going to treat this compound with ozone in the first step, and then DMS in the second step. And the bond that we're going to break is going to be this bond right here, right? So what we're going to end up with is a 5-membered ring. Look, 1, 2, 3, 4, 5. Okay, so we're going to draw a 5-membered ring. And if we number it like this, if we go 1, 2, 3, 4, 5, on carbons 1 and 4, we're going to have one carbon attached. That would be this carbon and this carbon. Right, so on carbon 1, we've got a carbon. On carbon 4, we've got a carbon. And each of them are going to have a double bond to an oxygen. So we end up with a double bond to oxygen here and a double bond to oxygen here. And that gives us an aldehyde in each case. And there you go. That's it. Now, keep in mind that both of these bonds are going on the exact same face of the molecule. So we actually end up with, well, that's not very pretty. We end up with a meso compound in this case. All right. So this is a meso compound. All right. So there you go. Oxidative cleavage. And again, if you want some more practice, you could look at Skill Builder 8.8. I highly recommend taking a look at that. So that covers all of the chemistry for this chapter, all of the new reactions. So what's your job now is to predict the products of addition reactions. Really, is this going to involve some memorization? Oh, absolutely it will, right? And learning all these reactions. It says you need to analyze the reagents. If it's ozone followed by DMS, you need to know it's an ozonolysis or an oxidative cleavage. If it's bromine and water, it's a halohydrin formation. If it's mercuric acetate followed by sodium borohydride, it's oxymercuration, demercuration, right? You need to know all these things. So you need to know the reagents, what groups are going to add. You need to know if it's Markovnikov or anti-Markovnikov addition. You need to know if it's syn or anti addition. And this is one of my major points right here, okay? Is that the more familiar you are with mechanisms and the reagents, the easier predicting products will be. Okay, so you've really got to familiarize yourself with everything in this chapter. And remember, what effort you put into this chapter will not go to waste. Okay, remember, everything that we learn in this chapter is going to show up in chapter 9, chapter 10, chapter 11. It's going to show up on organic too. So all of these reactions are crucial. So, you need to know all the addition reactions from this chapter, but you still have to keep in mind all of the substitution and elimination is SN1, SN2, E1, E2, because those are very pertinent in this chapter as well. Like, let's say you wanted to do this synthesis here. You'd ask yourself, is this a Markovnikov or anti-Markovnikov addition of water? Could anybody answer this? Well, I think it says it here on the slide, but this is a Markovnikov addition, right? So you'd need to know that all you need to add in this case is H3O plus. You should even be able to draw the mechanism of the reaction and say, well, if we've got a hydronium ion, it looks something like this. So the rich are going to get richer like this, and I'm going to form a carbocation, and that carbocation is going to be tertiary. Okay, it's going to look like this. It's not going to undergo any kind of rearrangement. So then we get nucleophilic attack, okay, followed by a proton transfer, and we end up with the final product. Right, you should be able to come up with that. And if you're saying, well, you wrote H3O plus, well, I've gone over this with you many times that when you combine water and sulfuric acid, what's the major species in solution is going to be a hydronium ion. Right, moving a functional group or a halogen around requires a solid knowledge of substitution and elimination. Right, you need to know your Markovnikov and your anti-Markovnikov addition. You need to know your hindered bases and your unhindered bases. Like, let's say we wanted to do this E2 reaction here. Well, there's two types of beta protons. There's the ones in red, and then there's this one in blue. We need to pull off the blue proton, so we would want to use an unhindered base to do that. Then we want to do a Markovnikov addition of HBr, so we would just use HBr, and we don't need any organic peroxides, right? So it just kind of goes over all the different rules and everything and how to do an anti-Markovnikov and all that kind of stuff. There's only so much yammering on that we can do about this stuff. You know, how to convert a hydroxyl into a good leaving group, right? You should know how to convert that into a tosylate using tosyl chloride and pyridine. And then you should know how to do Hofmann elimination with a hindered base So there's nothing really new there. Moving a pi bond around, that's something that we covered even in the elimination chapter. So now that we've got addition, we can bring that in. And so, really, what do you need to know? You need to know this. You need to know all of these reactions, frontwards and backwards. So if we just review them, the first one, okay, reaction number one is hydrohalogenation. This is a Markovnikov addition. You do need to know this mechanism, so I'll put a star by it. The second one is anti-Markovnikov hydrohalogenation. You do not need to know the mechanism of this. It's covered in chapter 10, so don't worry about it for now. The next reaction to form this alcohol, that's Markovnikov addition of water across a double bond. You definitely need to know this mechanism. You do not need to know the mechanism of oxymercuration, demercuration, but you should know that we use this. What for? We use this to avoid carbocation rearrangements. So I'll just put that there. The next one is anti-Markovnikov addition of water across a double bond. You should know that this is syn addition, okay, and that it's anti-Markovnikov. The next one is hydrogenation. You don't need to know the mechanism of it, but you should know that it's syn addition. So we could put here syn, okay. The next one is bromination. You should know the mechanism of bromination. You should know the mechanism of bromination and know that it is anti-addition. The next one is halohydrin formation. You should know the mechanism of halohydrin formation, and you should know that it is anti-addition. The next one is dihydroxylation with a peroxy acid and aqueous acid. You should know the mechanism of that reaction, and you should know that it is anti-addition. The next one is either one of these. It's going to be syn addition. So this is syn addition, and there's several ways to do that. And you don't need to know the mechanism of that reaction. And the last one is oxidative cleavage, and there's no syn or anti there to even worry about. So there you go. That is all the material that we covered in this chapter. And so now what we want to do is, practice using these reagents. So I would recommend printing this page, and this is just a suggestion. It's not an order. Okay, print this page, but I would print it maybe 10 times and practice filling in the reagents over and over. You would say, step 1 is ozone, step 2 is DMS. Right, for this one, you could use osmium tetroxide, a catalytic amount, followed by, or with NMO, excuse me. For this one, you would use a peroxy acid, followed by aqueous acid. For the next one, you would use bromine in water, et cetera, et cetera. You want to practice doing these over and over. You can definitely not bring this into a quiz. Definitely not. Okay, absolutely not. You have to have all the reactions in your brain, okay, for a quiz. So cannot bring to quiz. Okay, definitely not. All right. So with all that in mind, I think we'll take another short break, and that'll give you a chance to try some of these practice problems, and then we'll come back and take a hard look at these. So the ones that I want to try today are, I want to do 8.39. I want everybody to give this one the old college try. 8.42. And we'll just start with those ones, and then we're going to go into the textbook. And there's a question that I wanted to look at. Just let me find it here. I can actually stop the recording and just tell everybody who's online. So, okay, the other